The James Webb Space Telescope continues to keep astronomers on the edge of their seats in 2025. Webb's latest series of images doesn't just offer us breathtaking snapshots of the universe, it shows us space in motion. This capability allows scientists to witness firsthand how light echoes shift over time and how gigantic cosmic dust rings grow larger and larger, unfolding a dynamic, ever-changing cosmos. Yet, Webb has not only provided astonishing visuals, it has also opened a direct window into the immense, previously hidden processes at play in our universe. Processes that, until recently, were completely invisible to us. At first glance, some of Webb's new images might appear nearly identical, almost like duplicate frames. But a closer comparison reveals the truth: the cosmos is in constant flux. One particularly captivating observation focuses on the double star system WR-140, located about 5,000 light-years from Earth. This system contains a Wolf-Rayet star, a rare and exotic stellar type. Wolf-Rayet stars, or WR stars for short, are not part of the usual stellar classification. Rather, they represent the exposed cores of massive stars that have shed their outer hydrogen layers, revealing intense, hot, and turbulent surfaces rich in helium, carbon, nitrogen, and oxygen. In the case of WR-140, Webb's infrared vision uncovered 17 separate concentric shells of carbon-rich dust. These shells are produced by the collision of intense stellar winds from the two stars in the binary system, which occurs every 8 years. Even more astonishingly, these dust shells are not static, they move at an extraordinary speed of nearly 1% of the speed of light, or approximately 2,600 kilometers per second. The observations provided more than just a spectacular light show, they yielded valuable scientific insights. Notably, researchers found that dust formation does not occur evenly across the system. Rather, they detected clusters that form delicate clouds, each roughly the size of our solar system. Despite their fragility, these structures play a vital role in cosmic evolution. Carbon, the principal component of these dust shells, is a foundational element for rocky planet formation and the chemistry of life itself. The carbon-rich dust created in such systems can traverse vast distances through interstellar space, ultimately contributing to the formation of new stars and planetary systems. Could it be that the mystery of the universe's origin points, its so-called universe breakers, is beginning to unravel? Webb's capabilities extend far beyond dust detection. It has also identified some truly puzzling objects that are challenging what we thought we knew about the early universe. For instance, the telescope has captured images of extremely early galaxies that, according to our current models, simply should not exist in their observed form. These galaxies, which formed only a few 100 million years after the Big Bang, already appear to be as massive as our present-day Milky Way. That shouldn't be possible, not if we follow the standard cosmological model. There just wasn't enough normal matter in existence at that early epoch to build such large galaxies. Initially, astronomers thought they had made a grave mistake in identifying these compact red objects. But subsequent analysis confirmed the observations: the galaxies are real, and their mass is not exaggerated. These findings plunged the field into a state of crisis. Some scientists even began to question the standard model of cosmology. The universe breakers, as they've come to be known, sparked serious debates about whether we need a new model to explain the rapid buildup of mass in the early cosmos. However, the tide may now be turning. A research team led by Dale Kaspsky has proposed an alternative explanation that could rescue our cosmological framework. Their conclusion: the mysterious light from these red dots likely doesn't originate from stars at all, but rather from black holes. Upon re-examining the spectral data of these objects, the researchers noted signs of very fast internal movement, up to 1,000 kilometers per second. Such patterns are more characteristic of matter orbiting and falling into black holes than of stars within galaxies. This revelation suggests that around 70% of the so-called universe breakers might not be galaxies at all, but growing black holes, known in astronomy as active galactic nuclei, AGN. In these scenarios, the observed brightness is caused by gas and dust heating up as it spirals into the black hole, not by starlight. This finding negates the need for unusually large amounts of matter in the early universe and hints at a new paradigm. Black holes may have grown rapidly during the early cosmic epochs and played a key role in galaxy formation right from the beginning. But does this discovery mean that the mystery has been completely solved? Not quite. There's another puzzle. These luminous red objects appear to vanish from the cosmic scene after about 1.5 billion years. The reasons for their disappearance remain unclear. Additionally, though these objects shine brilliantly in visible and infrared light, they emit very little X-ray radiation, an unusual trait for active galactic nuclei. Normally, such black holes give off intense X-ray signals due to high-energy interactions in their accretion disks. The absence of this radiation only deepens the enigma. Meanwhile, Webb has also provided new insights into the dramatic deaths of stars. On December 23, it captured the remnants of a star that exploded as a supernova in the year 1680 in the constellation Cassiopeia, roughly 11,000 light-years from Earth. This aftermath is known as Cassiopeia A, or Cass A for short, and it has become a central focus of astrophysical research. Thanks to Webb's keen infrared capabilities, scientists are now able to see intricate structures that had previously remained hidden. One of the most spectacular features of these images is the so-called light echo. This phenomenon occurs when the light from a supernova reflects off surrounding interstellar gas and dust. The radiation can energize this material, causing it to glow independently. Webb captured these glowing regions in stunning detail, revealing swirling layers that resemble the grain of wood. Jacob Jensen, the head of the research program, expressed the team's amazement. "We were quite shocked when we saw this level of detail." His colleague Josh Peak added, "We see layers like an onion. We think that every dense, dusty region we see, and most of those we don't see, look like this on the inside." These findings allowed researchers to map the 3D structure of the interstellar medium for the first time in human history. Some of the most impressive discoveries included densely packed leaflet-like formations on an extremely small scale, about 400 astronomical units. To put this into perspective, 1 astronomical unit, AU, is the distance from Earth to the Sun, approximately 150 million kilometers. Though this may seem vast by earthly standards, in the cosmic context, it's surprisingly small. Even more intriguing is the suggestion that these tiny structures may be influenced by interstellar magnetic fields. The previously mentioned wood grain-like patterns could be magnetic islands, embedded within the otherwise streamlined magnetic field of the interstellar medium. These insights could revolutionize our understanding of cosmic dust, magnetic forces, and star formation in ways previously unimaginable. As Josh Peak pointed out, the way scientists study the interstellar medium will fundamentally change from this point onward. In yet another remarkable finding, Webb has studied a small, quiet galaxy that holds big secrets. Located roughly 5.3 million light-years from Earth, the dwarf galaxy Leo P, short for Leo Peculiar, doesn't directly interact with the Milky Way, yet it's close enough that individual stars can be studied. A research team led by Kristen McQuinn of Rutgers University used Webb's near-infrared camera, NIRCam, to observe about 15,000 stars within Leo P. They analyzed their colors and brightness to reconstruct the galaxy's history, and what they found was astonishing. Leo P star formation history reveals 3 distinct phases. The earliest burst of star formation ended about 12.6 billion years ago during the epoch of reionization. Then, unexpectedly, the galaxy took a 2.5 billion-year break before resuming star formation, activity that continues to this day. So far, only 3 other galaxies have been found with a comparable evolutionary pattern. Interestingly, all of them, like Leo P, are isolated and not gravitationally bound to the Milky Way. This may be the key. In contrast, non-isolated low-mass galaxies in our neighborhood did not experience this 3rd phase of star formation. But what reignited stellar birth in Leo P? One theory suggests that it may have passed near low-density gas or neighboring galaxies, triggering a reaction that fueled new star formation. Another hypothesis is that Leo P merged with another dwarf galaxy, and the resulting gravitational disturbances kicked off a new cycle of star birth. This is Space Lab, where the universe comes to life. Stay curious.